All right, so whenever we look at when picking up where we left off yesterday, when a would be a fraction, like 1/2, 1/3, 1/4, that's the same thing as the square root. Because if you remember with what we did yesterday, we were talking about when it was a power function, which was x to the a. So our a stands for an exponent. So if I have x to the 1/2, that's the same as the square root of x. X to the 1/3, the same as the cube root of x. And x to the 1/4 is the same as the fourth root of x. So our first one is the square root of x. And when we look at that graph, you'll notice that it's only on the right side of the y-axis. And that's because you can't take the square root of a negative. So it's going to be going up and to the right. Our domain is from 0 to infinity. And our range is also from 0 to infinity. If we look at the graph for x to the 1/3, or the cube root of x, you'll notice that we actually have a dip down here, and it's the full graph going from negative infinity to infinity. That's because we can't take the cube root of a negative number. So anytime it's an odd number, we can take that root of a negative. If it's an even number, we cannot take that root because you can't take an even root of a negative. So it's the same basic shape. The only difference here is that on the left side, it's going to be going down and to the left. And it's actually reflected across the line y equals x. Actually, that's not true. It's reflected around the origin. We don't actually need to know that part so much, but I am recorded currently. It just wasn't up on this screen. Good. All right. For whenever we would have one like x to the 3/2, which is where all we're doing is it's still taking a square root, but it would be like x to the 3rd and the square root of that. So if we do it that way, then it's going to be going up and to the right. And then if you have one where it's x to the 2/3, that's where we're squaring it, and then take the cube root. It's going to make this bird-looking shape when you were a kid and didn't know how to draw. So you drew a bird like that. That's the shape that's going to make. Again, for the 3/2, because our denominator is an even number, it's going to be going from 0 to infinity for our domain and our range. For the 2/3, because it's a positive even number on the top, where the 2 is, that's going to create our y values always being positive. Any number squared gives us a positive number. And then our domain is going to be from negative infinity to infinity, just because there's no numbers that can be ruled out. Next up is polynomials. So a function p is a polynomial if we have a function p of x where it's just different exponents. So this could be anything really. It could be x to the 4th plus 4x to the 3rd plus going all the way down to where we just have a number. So as long as n, or your exponent, is a non-negative integer and the numbers are real constants, which are called the coefficients. Then n is called the degree of the polynomial. So the highest power is the degree of the polynomial. Polynomials that are degree 1 are linear. If it's degree 2, it's quadratic. And if it's degree 3, it's cubic. Rational functions. The rational function is a quotient or ratio of two polynomials. So it's one polynomial divided by another. The domain of the function is the set of all real numbers x such that q of x cannot be equal to 0. So I can't have a 0 in the denominator. So my bottom function cannot be equal to 0. And we'll figure out exactly what that means here in a second. So whenever we look at this function here, this is an example of a rational function. And we need it to be true only whenever the bottom is not equal to 0. So in order to figure out where it's true and where it's not true, we're going to actually take this bottom part of the equation and set it equal to 0. So then by doing that now, I can factor this out. Or if you don't remember how to factor, you can use the quadratic formula. But I can factor this out to figure out when this would be equal to 0. So in order to factor, we need to figure out what multiplies to give us x squared, which would be x and x. Then what multiplies to give you 6 and adds to 5. Would be 2 and 3. And from here, we break this up now and do x equals negative 2. That's just by doing x plus 2 equals 0. Then you do x plus 3 equals 0, subtract the 3, and x equals negative 3. So then by finding out where it's equal to 0, I can say the condition for this is that x cannot be equal to negative 2 or negative 3. Because if it is, it gives me a 0 on this denominator. Yep. Yeah, we're just finding where it can't be equal to 0 currently. I mean, granted, it can't get more complicated than that going back to like algebra 2, but for the current situation, that's all we're looking for. It's where the domain exists at. All right, moving on to our next stuff. We have algebraic functions. An algebraic function is a function constructed from polynomials using algebraic operations. This is addition, subtraction, multiplication, and division, and taking roots. Rational functions are special cases of algebraic functions. Then we have trigonometric functions, which we'll go over more in depth in section 1.6. But here's our basic graph of the sine function. It starts at 0, and at pi over 2 goes up to 1, then back down to 0 at pi. And you don't have to draw these graphs either, just because we are going to go into those more in depth in section 1.6. So Moving on to exponential functions. Exponential functions are of the form f of x equals a to the x. That's where a is greater than 0, so it can't be a negative number, and a is not equal to 1. An exponential function will never have the value of 0, and the range is always between 0 and infinity. So it never goes down below the x-axis. And I would draw these graphs, at least just one of them. Like I'd just do the 10 to the x graph. And then over here, 10 to the negative x. Last type is a logarithmic function. These are the functions that are of the form f of x equals log base a of x, where a can't be equal to 1. So if you look at a logarithmic function, it might remind you of an exponential function. It's just like going the opposite direction. It starts at the negatives and then comes upwards and flattens out. So that takes us to increasing and versus decreasing values. If a function is climbing or rising from left to right, we say it's increasing. If it's falling or descending from left to right, we say that makes it decreasing. So if it's going up from left to right, it's increasing. If it's going down from left to right, it's decreasing. We can pick up here tomorrow, Mary. We'll just start with this page because you won't need any of this for your homework. You're basically just going to be identifying concepts on homework. So.